Okay, so I think we can start. Welcome everyone, thanks for joining. We are the organizational team here, so I'm Sophie from Most H2. We also have every other project here, and I would now give over to our moderator, Lenka, who has kindly agreed to moderate this webinar. Just beforehand, please, you can all write in the chat if you have any questions or comments. We will also observe the chat. It's just that we want to keep it for the speakers and for the moderator more simple if we just go through the agenda, because we also have not so much time. But please just write into the chat in any time, and we can always also address these questions at a specific time point then. So please, Lenka, you can start. Yeah. And thanks for everyone.
Yeah. Hello, good afternoon to everybody. Welcome to this joint webinar on SE or more exactly environmental impact and sustainability of hydrogen storage and production, focused on the SCA insights from the European projects related to hydrogen production and storage. So as you may know, SCA is a multi-criterion and multi-stage methodology for evaluation of environmental impacts, be it of a process, a service, object, or system. It's also a standardized methodology. And through this webinar, we would like to focus on the hydrogen production and storage, using the example of 4 different projects that are related to this topic and that are financed by the Horizon program. So the objective is to identify and discuss some common challenges, solutions between the related projects, and offer an overview to the scientific community and the industrial hydrogen sector on the current status and development on the SCA studies based on the project funded through the Horizon program. So we will have 4 different projects that will be presented.
Do we see the slides? We cannot see.
No, I have just a black screen.
We cannot see it.
Me neither as well.
So I will continue a little bit on the time that the problem is fixed. So we will have 4 different projects: Master Boost, Most H2, Hydrem, and MEF2 H2 that will be presented. But before, we will have a keynote presentation by Ashrakat Hamid from Green Delta. So if Ashrakat is ready, we can maybe start by her presentation. Now it's okay for me. I have the slides.
All right, perfect. First of all, thank you for having me and for making this webinar. I think it's quite useful and relevant to today's topic. And I will start with sharing my slides. So let me know if you are able to see my presentation. 1 second. Yes. So are you all able to see my slides?
Yeah. Can you put it full screen?
Is it full screen now?
No.
Oh, no, yes. It's not. Oh, okay.
It's not the presentation mode.
1 second. Stop sharing. Share. Maybe if I share my second entire screen, that'd be good. No.
No. Yeah, perfect.
Yeah.
Perfect. Okay, great.
The floor is yours.
So, thank you so much. So my name is Ashrakat, and I'm a sustainability consultant and researcher at Green Delta. You might have heard about us because we developed the software OpenLCA, which is a prominent LCA software, open source software. And in today's presentation, I'll be talking to you a bit more about the importance of the harmonization LCA, which is relating to a project, an EU project, which we have completed last year. And I will jump into important outcomes that we had and applicable outcomes that could be relevant to presenters and attendees today. So starting off, a bit of an intro, we all know how relevant it is to have the hydrogen production, and recent reports have always project the demand is increasing with time, and hence to be able to meet this demand, we ought to, of course, try to produce as much. However, the question is producing in a more eco-conscious way. We have the hydrogen value chain over here. There are multiple ways to produce hydrogen, but the most common way is through the steam methane reformer. There are many ways to store hydrogen, which is many of the projects are clearly researching extensively to find out the most efficient and environmental way. And there are, of course, ways to distribute it. And of course, hydrogen comes into extreme use stages, such as through the feedstock for the ammonia or the transportation or for other industry uses. So which pathway should we use, or which distribution or which channel should we use? That's why we perform LCAs, to investigate which pathway or which production technology has the minimal impact. However, there are, yes, many LCA studies taking place and published throughout the internet. However, the problem lacks in the comparability. So let's say if we have hydrogen coming from, produced from steam methane and from biomass gasification. However, the system boundaries, or how the function unit was defined in the first place, or the method even used to calculate the impacts, if they're not the same, then it's difficult to confidently say which production technology or which storage technology is fitting or the least environmental impacts. And that's why we call for the harmonization protocol to calculate all these impact categories, to define the system boundaries, and to clearly define the functional unit with time, which means we call for more harmonization. And this is why we had this project last year, which concluded, which is about the Sustainable Hydrogen Guidelines for Life Cycle Sustainability, which brought together the following partners. And it was a fund not only by the EU, but also by the Clean Hydrogen Partnership, to develop guidelines that are more, that encourages more harmony amongst the LCA practitioners when they try to conduct LCAs for their fuel cell or hydrogen systems, so that it can be easier to benchmark and to drive robust decision-making over time. The project outcome resulted into the following guidelines, which are available to download, not only on the LCA field, but also in the life cycle and the social LCA, and also a harmonious or complete comprehensive guideline on the life cycle sustainability assessment. And finally, we also presented a open source tool for users that can use to kick off their projects in the hydrogen production if they feel like they need some guidelines on how to use the guidelines practically. The tool is one of the ways to do that. And then this is just focused now on the LCA, the environmental LCA, since this whole topic is about. The guidelines basically focus on many things. So we cover all the 4 main stages of the LCA. We dive in depth into also how to modeling approaches for prospectivity, and especially because it's very important that hydrogen technologies are still not existing. So how to assess prospective technologies, in this case, multifunctionality, which is also very common in many hydrogen production cases, or how to handle it. The guidelines are basically guided with 3 types of boxes, meaning there are requirements, there are recommendations, and there are also supplementary informations. And we also rate the method readiness level of each thing that is guided and supported. We talk about the following system boundaries. We cover not only cradle to gate LCA guidelines, but rather cradle to 6 gates, which we define based on the hydrogen production stages. So hydrogen production is not only about producing the hydrogen, but rather purifying it, compressing it, transporting it, storing it, and distributing it. So each one of these are actually gates, and more or less they're not done in one shot, but rather done in many levels. We also extend the guidelines to cover the production and use stage, of course. So we cover also the use stages, which is cradle to grave. For example, one of the most common things that we discussed and we wrote very extensively is how to define a proper functional unit. So for example, we say here, for hydrogen productions, functional units should contain the hydrogen purity, the pressure, the temperature. They all must be specified so that they are comparable across different systems. And if you're going to use your hydrogen for transportation, then you have to represent the distance traveled. And then, for example, this is an example of the guidelines obviously came with applications. So we had applications for the guidelines, and this was an example of the function unit for the hydrogen for the PEM production base that is used in a fuel cell electric vehicle. Also, we talk about the importance of the capital goods inclusion into the guidelines. And on the right-hand side here is, again, results of the applications that we had. So basically, we see that how one of the storage system in this project that we implemented, which was a present case study, was the Type 4 hydrogen storage tank at the pressure of 700 bars. And we see here the impact of the hydrogen tank is much, much higher than the other components or capital components of the powertrain in the car. To facilitate and to make this easier for example users to use, we implement all these guidelines into an open source software, and the objective is to facilitate them. The tool is available online. The case studies that we apply, not only on the production phase, but also we compare different systems, like for example, solid oxide, and also we compare the PEM production pathways for the hydrogen and different use stages. So these are all presented in case studies and applicable. And the whole, again, objective is to, yes, we have technologies that provide everything, but to drive the right decision, we ought to have harmonized, comparable hydrogen LCA product systems. And yes, I thank you all for listening and for your time.
Thanks very much for the very clear presentation and for keeping the time, which is also very important. I propose to continue directly with our different projects presentation, and then we will have 45 minutes for the roundtable, where all your questions could be also answered. So let's welcome Javier Saez from the first project. So MasterBoost, I will let you present rapidly the project and specify what is your approach for the LCA of your developed solution. So the floor is yours, Javier.
Yeah, thank you very much, Lenka, for the presentation, for the introduction. My name is Javier. I work for Contactica. We are a small consulting firm which participates in different EU projects. We do tasks of communication and dissemination, but we also have a sustainability department in which we carry out sustainability assessments of different projects, such as, in this case, a MasterBoost project. So I will first give you an overview of the motivation of MasterBoost and what we aim to achieve in the project. Can you move to the next slide, please? Yeah, perfect. So the main motivation of the project is due to the fact that the transportation sector is responsible of approximately 30% of the greenhouse gas emissions in Europe. So hydrogen is seen as a solution, as an alternative to decarbonize the sector, because it does not involve the combustion of fossil fuels, so it does not entail any CO2 emissions. But the main drawback of hydrogen, which hampers its implementation, is the low energy density per volume of hydrogen, which requires larger volumes to store hydrogen, and it usually requires around 700 bars compression, and it achieves a storage capacity of 25 grams per liter of volume. So the main objective of MasterBoost is to develop ultra-porous materials, mainly activated carbons and aluminium and iron metal organic frameworks from secondary sources. This is from recycled materials, to enable the storage of hydrogen by absorption in these materials, to store hydrogen at higher densities and lower pressures around 100 bar. So the main goal of the project is to build a tank, a hydrogen vessel of at least 20 liters, which will be able to store at least 33 grams of hydrogen per liter of the system. For that purpose, the project is divided in 4 different stages. The first one is the development of the materials at laboratory scale. Then the second one is the development of the materials at a greater scale, at a pilot plant, let's say. Then the other stage is to build the hydrogen vessel. And finally, our task is the evaluation, both economically and environmental, of the system, of the technology. So for that purpose, our LCA approach, can you move to the next slide, please? Now, our approach follows the international standard organization rules, which is divided in 4 different stages of the LCA, as you may know. We are doing 2 different life cycle assessments. On the one hand, we are doing a cradle-to-gate approach, which evaluates the extraction of the raw materials, the transportation, and the processing and the production of the ultra-porous materials. In the future, during next year, we will do also the cradle-to-grave LCA, in which we will evaluate the suitable storage of hydrogen, the building up of the hydrogen tank, and the end of life and the regeneration, if necessary, of the materials. But so far, as we lack those data, we have only studied this cradle-to-gate analysis. We are following the product environmental footprint method, which gives us like 16 different environmental categories. And we are also carrying out not just the life cycle assessment, but we are also following a life cycle costing, which follows the same system boundaries as the LCA, expecting also to evaluate the economical viability of the technology. If you move to the next slide, please. Yeah, well, this is the life cycle costing, which we are evaluating it by estimating the net present value of the technology. For that, we are also, well, I will comment now how we are doing that, but we have also to estimate the capital costs, which is not easy. If we go to the next slide, I can discuss briefly about the main challenges that we have found regarding the LCA and the LCC of the project. The first challenge was to select the suitable units, because ideally we should choose 1 kilogram of hydrogen or 1 megajoule of hydrogen as the ideal functional unit. However, as we discussed before, the storage capacity, it also depends on external conditions such as temperature, pressure, the geometry of the tank, or the purity of hydrogen. So one alternative is to propose as functional unit 1 kilogram of hydrogen stored at specific conditions. But for our case, for instance, in MasterBoost, as we did a cradle-to-gate approach and we did not evaluate yet the storage and the compression and so on of hydrogen, we only evaluated the production of the sorbent materials. So we propose different properties of the materials, such as the BET area of the pore volume, as functional units, because we have thought that these properties represent better the ability to absorb hydrogen better than just a physical volume unit. So this was the first challenge that we found regarding the LCA. Other challenges that we found in the next slide are the finding data gaps and uncertainties. If you move to the next slide, please. Yeah, we found 2 types of uncertainties. The first one is related to the data gaps when carrying out the laboratory scale experiments, because most of the times the technicians at laboratory have difficulties to measure or to quantify all the inputs and outputs of the process. We have also found that most of the times it is unfair to compare a laboratory process, which is always performed like a batch process, against a continuous industrial process, which gives you more opportunities to recycle materials and to minimize energy, water, and chemical consumption. So for that purpose, to reduce this uncertainty and to improve the accuracy of the study, we are using modeling tools such as Aspen Plus, which can be an effective solution to simulate the industrial performance of a large-scale process. The second type of uncertainties that we found come also from the assignment of activities, such as the energy source, the potential modes of transportation, the distance, the prices, and so on. So to deal with that, we are carrying out sensitivity studies on both continuous and discrete variables. On continuous variables such as the price of energy and electricity, and also on discrete variables such as the type of the origin of the energy, the use of water, and so. So with these scenarios, we are hoping to reduce the uncertainties and to allow the reproducibility of the study. I guess we will discuss about this on the roundtable. So I will pass the floor to the next presenter.
Exactly. Thank you very much. So the following speaker will be from the MOST H2 project. It's Dr. Konrad Spindler from Green Delta. So Konrad,
Hello. Yeah.
the floor is yours.
Okay, thank you. Yeah, I'm Konrad Spindler. I'm also working for Green Delta as Ashrakat, the developers of OpenLCA, and we are also involved in a lot of European research projects. And so I will now take 5 minutes to briefly tell you what is the MOST H2 project about, and I will mainly focus on 2 of the most important findings to tell the LCA community, let's say. It's not about end results, it's more about findings in the modeling. So here you can see the overview of the MOST H2 project. That here we have also work packages involved who started in the beginning to develop machine learning databases to predict MOF structures. We have work packages and partners who then do the lab scale synthesis of very new MOF structures with high volumetric and gravimetric capacities. Then MOF structures are chosen for scale up, so for a pilot demonstrator tank. And this will be integrated into a roughly 10-liter tank as a demonstrator in the project. And we also have attached a feasibility study where partners do a techno-economic assessment because, for example, a railway application where you cannot electrify the trains could be a feasibility, and there is a study done for this. And we at Green Delta, we are responsible for the full life cycle sustainability assessment. So we start from the lab scale and go over to the cradle to grave by the end of the study, including life cycle assessment, life cycle costing, but also social life cycle assessment. Okay, the next slide, please. Comes with a delay. You can put already all the points because I think I put yes by. So this is just some fact sheets. So the MOF production, we do a cradle to gate study. This was the main focus of the first years of the projects because, of course, for a cradle to grave study of the whole tank system, we need already having a tank available or at least designed. So the MOF production cradle to gate, then the whole tank system cradle to grave, including social and costing. The method we choose is, as most European projects nowadays, the environmental footprint method from the JRC, from the Commission. The EcoInvent 311 database we use in the background. Of course, we started with lab data, which is one of the biggest challenge of these low TRL projects, that you in the beginning have only lab data available, and then we do kind of predictive LCA by upscaling it with values, parameters we have from literature, which is here in the brackets shown. And we also use some all tools from ETH Zurich, like FineChem, we modified a little bit. EcoSolvent tool, the Tankinator is not old, that's from the US, to get estimations, rough estimations of, for example, the linker, the tank, so that we have benchmarks. And now we go into the last year where, of course, we also take direct primary data from our upscaled demonstrator tank and include this directly in our models. The next slide, please. Yeah, here you can see an overview. I put this slide so that you can see that already the MOF production can be quite challenging and complicated, because usually you don't have the data available in commercial databases. So you have to decide how far can you go with time requirements and accuracy. So for some process step like mixing heating, we do process calculations because we know the exact temperatures and we can estimate industrial sized reactors to do that. For like metal precursors, which are simple metal salts, we can do simple stoichiometric calculations for the LCA, because this is a rather easy to produce product. And and the solvent recovery, this is very important at the moment. There we are using proxies to estimate the impacts from a distillation in a chemical plant, because as you will see in the next slide, that the solvent is important for the MOF production, of course, only when you do a solvothermal synthesis. So in most H2, we produce the MOF with solvothermal synthesis, where you need solvents. The next slide, please. We should see there some calculated results exactly. And this I show you. So this here is the single score of some MOF production. The single score is from the environmental footprint method, a score which aggregates all the environmental impact categories into one number for easier dissemination. But here it's not so important to look on the absolute values. It's important to see that when you on the x-axis, so it's like a result matrix with different scenarios. And when you decrease the reactant mass intensity, so that means you need less adducts, less materials in the input to produce your MOF, you are not really changing so much the environmental impacts, because most of your impacts depend really on the solvent, how much solvent you use. At the bottom, the red ones, there is a solvent mass intensity, so 150 times liters of solvent for 1 kilogram of MOF production, which comes from the lab. This is what is lab data, and you can see the lab, of course, really overestimates reasonable industry data. And then I chose there 20 liters per 1 kilogram of MOF production, and you can see this has a huge impact. It's a factor of 6 lower. And of course, if you even recover then some of the solvent and you feed it back into your production system, you can even get lower. So this here is to highlight that whenever you have a thermal synthesis, you need to really focus on what to do with the solvent. Because often in literature, you only find the easy simplification, okay, we just take 10% of the solvent, we assume 90% recycling, and that's it. Okay, the next slide and last one, I think. There you can already put down all the numbers, yes, because for a full cradle to grave, I also want to highlight here the functional unit that we chose, so which is storing and releasing 1 kilogram of hydrogen with daily refilling and a reference service life of 20 years. So this 20 years, this is of course variable. I just want to highlight that the functional unit of the whole system needs to consist of the lifetime of the tank. How often do you refill it with hydrogen? And of course also what is the conditions, like what's the pressure, what's the temperature? And you can then choose the system boundaries to include the MOF, the tank, compression cooling in the use phase. And the question is, do you include the hydrogen also when you only want to investigate the storage system? And at the very bottom, I show you an exemplary contribution. So this is when you calculate the results for the greenhouse gas emissions. And when you don't put any H2 into your supply chain, so you just look at the storage system as a whole, then you will see that, okay, compression cooling, nearly 80% of the impacts, and the MOF 20%. But as soon as you include the hydrogen and even the greenest one, so here I choose green hydrogen from a renewable energy supply for electrolyzers, then you will see that the MOF and the tank will only have 4%. And this is kind of a good news, because it means that even if we put the MOF into our tank, it will, over the lifetime of the whole system, not drastically change the environmental impacts, because most of them is defined by the hydrogen itself. Okay, thank you for your attention.
Thanks very much. So there's one hand raised, but I propose to finish the flash presentations and then go back to the questions before starting the roundtable. So we have now the HyStream project presented by Freddie Liendo from HySysTech. So please, Freddie, the floor is yours.
Hello, everybody. So, yes.
Just a minute, I need to make sure that I have the.
Otherwise, I can also share it if not an issue.
If you have it, yes, please go on, Freddy. You can share your screen.
Okay, let me know when you can see my screen.
Yes, perfect.
Thank you.
Okay. Well, hello, thank you for the introduction. Yeah, I'm Freddy Liendo from EasyTech. I will present the project HyStream, so hydrogen storage and transport using ammonia. That is a European project, H2020, funded by the European Union, and it's focused on the hydrogen storage as and conversion into ammonia. So the project is based on the challenges from hydrogen to ammonia in terms of storage and transport of the hydrogen that are one of the main objectives of the project itself, in which we are trying to develop a short storage system at high pressure, and the storage of the ammonia as ammonia. So we practically are developing physical hydrogen storage material, enabling short-term storage, and a flexible low-pressure ammonia synthesis system, seeking on decreasing the retaining content catalyst, high-pressure temperature ammonia sorbents. So trying to also developing an induction heat and support that allow us to have the synthesis, the ammonia synthesis under more controllable and sustainable conditions. So the aim is to demonstrate, as I said, a compact containerized ammonia synthesis system. Ammonia synthesis based on two main consecutive stages. So that is the first of all, we'll have the storage of hydrogen in a vessel at high pressure that allows to store and buffer in the hydrogen produced from an electrolyzer using an ultra-porous material that has been developed within the project. And then we'll have the ammonia synthesis reactor with an improved Haber-Bosch process where the stored hydrogen react with nitrogen forming ammonia. And we are using here new catalysts and sorbents developed by the HyStream consortium. So The main objectives are the development of functional catalysts and solvent materials for ammonia synthesis that they can coexist in the same reactor. So having then like layers of catalyst and solvent in order and that these materials can operate under the same conditions of temperature and pressure in order to be able to continuously absorb the ammonia formed and let's say splitting the equilibrium towards the formation for more ammonia. This should entails a higher single pass conversion in comparison to state of the art Haber-Bosch process. So then we have the development of the new ultra-porous materials for high hydrogen capacity and realization of the lightweight composite vessel for physical absorption and hydrogen storage, in which the new ultra-porous materials will be placed, so to have the short-term hydrogen storage system. Then the other objective is the design, construction, optimization, and demonstration of dynamically operated packed bed reactors for ammonia synthesis using the functional catalyst and solvent materials. So based on their kinetics and the thermodynamics of the system, we have designed and built the demonstration unit. The demonstration units will be developed, demonstrated. The prototype will be operated, and the Histran technology will be demonstrated at TRL5 in the coming months, which will allow us then to do the validation of business cases and in addition, during the project, we'll have the modeling of the system at different levels, so quantum level, microkinetic level simulation of the reactor, higher level simulation for the reaction and process with machine learning and AI, and process level simulation in order to have more results and integrate more scenarios to the demonstration campaign that will carry out in the oncoming month. So this will allow us to that all the aspects will be considered and make possible a more robust results for the assessment of the technology at the end of the project. So regarding to the specifically to the LCA, the LCA of Hyster has a dual scope. First, we have the LCA for the material, so the MOF, catalyst and solvent that has been analyzed, and then later we'll have the LCA for the pilot plant. So far, we have defined the goal of the analysis for the materials, so on the hotspot, to implement mitigation measures and compare the materials to determine which had the lower impact. And to achieve this, the methodology goal and scope was defined, data was requested from partners, and the analysis was conducted. This has been carried out, let's say, in lab scale, and we have tried to fill the gap between this and which has to be actually the reality for the implementation of them. So the scope of the art was also sought because the partners developed two designs for each materials, and the comparison was between them. Then for the pilot, the approach will be similar. So, but in this case, we need to define a benchmark scenario. Basically, it will be one of the scenarios will be the decentralized ammonia production that will be, let's say, or scope. And for example, in for all the materials and for the pilot, all the calculation has been carried out considering 1 kilo of ammonia produced. So today we are here and trying to integrate the data that we have with what is already in the state of the art.
Freddy, can you wrap up rapidly, please? Because we are running out of the time.
Yeah, I'm finalizing. Yeah, sorry. So as the main challenge that we have now, it's the trying to adapt the data referred to different scales. So in order to have more reliable data and fill the data gaps because some data is protected or anything. So we need to try to fill these gaps and then create the final LCI for the state of the art. So trying to have the benchmark for the analysis of our technology. So this is all from Houston Project. So for more details, you can contact me or Esther or the coordinator that is Vincenzo Liso from Aalborg University. Thank you.
Thank you very much. So before going to the roundtable and to the questions, we have the fourth speaker with us from MOF2 H2 project, Dr. Pranav Nakhait from Maastricht University. So the floor is yours. Please try to keep the time to let us some time for the discussion.
Yes, thank you. Compared to other projects, we are relatively at the initial stage. So I'll be quick, no worry about that. So hello everyone, I'm Dr. Pranav Nakhate and I'm assistant professor at Aachen Maastricht Institute for Bio-Based Material, associated with Maastricht University. And we are associated in this project as a sustainability partner. So this is kind of an overview of what we are doing. The focus is on developing the sustainable method of producing hydrogen using metal organic framework. So a bit of a background, as we all know about hydrogen and its application, wide application and so on, that's great. But what about its production? So current hydrogen production is mostly through, steam methane reforming. But there are some consequences with steam methane reforming. I'm not going to go in detail, but as you know, there are CO2 emissions and so on. Also, there are some new methods like electrolysis and other cleaner technologies being introduced. But again, the costing is one of the important issue with such techniques. So hence, this consortia came up with an idea of photocatalytic water splitting, where we can capture the solar energy and then convert it into the hydrogen itself. If you can go to the next one. Yes. So here I'll just give you brief project objectives. So the project objective is basically threefold. It's developing a photocatalytic using water splitting and using MOF as a catalyst structure. And to achieve at least 5% of conversion efficiency, and then of course do that all within the sustainability framework, both in terms of environment and cost taking into consideration. The scope is to synthesize and optimize the second generation of MOFs, which is the critical part, as many of the previous authors, speakers mentioned already. Then integrating MOF into the lab scale demonstration and scaling up is one of the tasks within this project. And then conducting the LCA and techno-economic assessment for this project is the final task or final objective of this project. Next one, please. Yes, so how exactly we're going to do that, or how exactly we're going to achieve that? So the method that we are using is the attributional LCA method. And for that, we are using presently CIMA-Pro as a tool to conduct this LCA, but also we're exploring different tools, for example, OpenLCA or Activity Browser. So that also we are exploring, and we are taking use of EcoInvent background database. For techno-economic assessment, we are using Aspen plus economic analyzer for that purpose. And this is cradle to gate system based on the database that we have based on the data that we have received so far. So we are conducting this cradle to gate analysis, considering raw material, MOF production, its lab scale testing, characterization, its scale up, and then the waste and solvent treatment methods. The functional unit is the production of 1 kg of hydrogen under the 1000 watt per meter square illumination. So this is the setup that we have for LCA as of now. And if you can go to the next one, just a brief information on the challenges that we face so far, because this is the important slide, and here I think I can get a lot of input from you guys who are actually progressed in your project. So data gap is the most important one that we faced. So for example, MOF degradation rates, yields, upscaling challenges we are facing at the moment. Lack of benchmark. There is no accepted LCM method for hydrogen, for especially photocatalytic hydrogen production. So the comparison makes it difficult. The scalability modeling, of course, all these activities are carried out at the lab scale. So scalability is one of the challenge, also mentioned by one of the speakers earlier. Then the impact quantification. Uh, but how to mitigate these challenges? Basically, we plan to do scenario and sensitivity analysis using Monte Carlo simulation and experts' opinion as well. And also we will do the modeling, modular modeling, basically for LCA and TA, just to allow it updating as TRL increases. So this is basically the challenges and lesson learned so far in our project. But like I said, we are at the initial stage, so the input given by the other speakers will be really helpful for us to develop the full-grown LCA model in the future. And if you go to the next one, just for the fun, just for the fun. So here, if you see, we all are selling, all the MOF2 S2 project partners, we are selling to a sustainability goal, and we take LCA as a compass to achieve our sustainability goal. So yeah, with that being said, I'll stop my content. Yeah.
Thank you very much. So our flash presentations are over. I've seen previously one hand raised. So before starting the roundtable, please ask your question.
Yeah, I think Marco had a question. I don't know if you are still online.
Or muted. Just in case, you can also write your comment in the chat.
So meanwhile, we have another question from Anthony Chopin asking a generic question. Is there a beginner's course or module at university on LCA and TEA? So I guess it depends. Yeah, please.
I think there are plenty of different courses on different levels. I think that Anthony is more focused on kind of MOOC, something which would be available online, I suppose. I don't know. I'm not sure. Maybe the other speakers have an answer.
I think if it's only about LCA and not about the modeling, because for the modeling you usually need a software, and then it's better to have a guided course or a training. True. But for standard LCA, maybe a textbook is sufficient, because a course will be then also just going through the slides with all the textbook knowledge. There's even a free LCA textbook, I think. Yeah.
Could be. Okay. Yeah, I agree. Okay. So if there's no other question, I would propose to start the roundtable. So the first thing we wanted to discuss during this roundtable was related to comparing the methods, methodologies, and tools that we or you used across your projects. So if you can just rapidly remind, because one of certain speakers has already mentioned the functional units, but just few words on the functional unit we've chosen, on the boundaries, the software tools, and the method that you've started to use, and why. Maybe starting by Javier.
Yeah, I should go first. So regarding, well, that was too much to comment. Regarding the functional unit, I think it depends on the point of view that what you want to compare your work with, no? For instance, in our case, as we have two different LCAs, one which is a cradle to gate, and the other one which aims to evaluate the whole system. So on the first LCA, we are using the physical properties of the sorbent material to evaluate the environmental impacts of the hydrogen storage without evaluating the hydrogen storage. For the complete LCA, yeah, we should. I think we all should aim to select as functional unit the amount of hydrogen stored at specific conditions at temperature, pressure, and so.
Okay.
What else
So
regarding
yours was a 1 kilo of H2 stored, is that right?
Yeah, we haven't done it yet, but we aim to use 1 kilogram of hydrogen stored. Yeah.
Okay. And the software tool you will be using and the method, the evaluation method?
All right. We are using the product environmental footprint method to calculate the impact assessment. And regarding the software, we are using CIMAPRO.
Okay.
But we are using EcoInvent databases and some secondary databases, Biosphere 3 also. But we are also researching or investigating the use of Python to do the LCA in Python code, so we can couple it, we can integrate it also with the modeling in Aspen, for instance.
Okay, perfect. Now, Conrad, you mentioned storing, if I'm right, storing and releasing 1 kilo of hydrogen on a daily refilling basis over 20 years, if I noted it correctly. You've mentioned also CIMAPRO. So why you choose this functional unit, and what are the advantages, disadvantages, and the method that you will use for the evaluation?
Yeah, I think if I remember also correctly, 3 projects use the environmental footprint method from the EU. Yes. So that makes already the method comparable. The functional unit that I wrote there was for the cradle to gate, so including the use phase.
Okay.
And I think there it is important. Ashrakat also mentioned that already with the SHE guidelines, that people at least know the lifetime, the pressure and the temperature, so knowing the conditions, right? Whereas when you only look at cradle to gate, a kilogram MOF or a kilogram H2 stored could be enough. I also want to comment on the cradle to gate, because most projects had a cradle to gate, that if 1 kilogram of hydrogen stored is the declared unit, it's not a functional unit anymore, because we have no use phase, no function, but declared unit. I think that's the best, because it includes the performance of a MOF, for example. But then one should also mention the gravimetric density or and the volumetric one, because then people can always calculate back. That is nice. If you have only report 1 kilogram of MOF, that's also fine, because people then can take their own performance, like the gravimetric density of the MOF, and calculate it for 1 kilogram of H2. I think it is important that whenever we publish something, that then people can use that. It's not only a black box, but that people can use it then with maybe their own performance data. Yeah.
Okay. Perfect. Thank you. And then for the Hydrogen project, Freddie, what was your approach? What is your software tool, and what was your methodology or method?
Yes,
Good.
well, in our case, we also use the eco-embed database using CIMA-Pro software. Can you hear me, right?
Yeah, yeah.
Okay. For
The functional unit?
it was everything was calculated for each kilo of ammonia. So
Okay.
even for the materials, how much material was needed to produce 1 kilo of ammonia. But in this part there was a lot of uncertainty because since this is a novel material and we are, let's say, in the developing phase, we actually don't know how much this catalyst could last. The same for the sorbent material. So how much material we need for the ammonia synthesis is I mean, for each kilo of ammonia, it's a sort of still, let's say, question because we need like more time to define the actual, let's say, lifetime of the material. So because if we consider commercial catalysts, they could last more than 10 years. So in that case, the impact of the material is lower. While in our case, they still have a lot of impact because we were considering between 3 or 6 months of duration. So that entails a very important impact, not only for the LCA, but also for the techno-economic analysis.
Okay,
And
thank you.
for the analysis,
yeah.
we use cradle to gate approach in both cases.
Credit to gate. Okay. Basically the same question for the last speaker.
Yes.
So the software to the evaluation method and how did you choose the functional unit?
Yes, yes. So I'll be as specific as possible. So basically, our functional unit, as I mentioned earlier, is 1 kilogram of hydrogen production based on the ideal solar conditions. We choose this functional unit just to be harmonized with all the existing literatures that we have observed so far, so that the comparison makes it easy. And secondly, our system boundary is still the production of hydrogen itself. I mean, of course, based on the data, we will include the usage and application phase further in future, maybe. But so far, we have till the production. And for that, like earlier, a person from Green Data mentioned, that the hydrogen production quantity makes more sense as a functional unit. So that's why we selected that.
Okay.
And this is the product till the production phase is our system boundary. And for software, like I mentioned, we are using CIMA-Pro as a software so far, but also we are exploring Activity Browser. And for data collection, mostly it is the consortia partner. So data collected from there. Secondary data as well from peer review journal. But again, we analyze that and we go through experts just to verify that data. And also we use process modeling like Aspen and all for the remaining data collection.
Okay. Thank you very much. All of you have mentioned the history of the boundaries, the system boundaries, and in some cases you have mentioned that you include the H2 production. In some cases, if I understood it well, you have excluded it. So can each of the speakers mention again and discuss this point? Include or not to include H2 production and why, and what are the advantages and disadvantages? Maybe Javier, we start
I
with
will go
you.
first.
Yeah.
Yeah, in our case, we have not included the production of hydrogen because I think it's not the purpose of our project. The purpose is to compare the storage of hydrogen through our method, let's say, through the use of activated carbons and MOFs. and compare it against other current storage systems, such as purely compression. So I don't think it makes, I mean, we could include the production of hydrogen, but I don't think it makes sense for the purpose of the project.
Thank you. Konrad, your point of view on this?
Yeah, I tried already to show in the presentation a bit the point, because our project is also focused only on developing the storage tank, right? Nobody of us is working in the hydrogen supply chain. Still, I think it's good to include it it can be included as a standard data set from a database or something like that, because when you include it, you will see what is the share of your tank impacts compared to the hydrogen impacts. Because it might be that you will make, in the very beginning, design decisions or think like, this impact is very high, we should maybe not use this material. But maybe in the end, the overall impacts of the tank to the hydrogen system is very small. So then this is important to know. And of course, cradle to gate, you don't need to include it because the hydrogen comes in the use phase inside. But in a cradle to grave, in my opinion, it should be included because also the tank, the function of the tank is not to be there and standing there. The function of the tank in the end is to deliver hydrogen somewhere, to a plant, to another system, to a fuel cell. Yeah. And as you could see, when I chose even the greenest hydrogen, the impacts of the tank are quite small.
Yeah, it was very clear from your presentation.
Which of course depends a lot on the lifetime, and this is another story. Of course, when you shorten the lifetime of your tank a lot, the impacts of the tank are also getting bigger.
Yeah, sure. Thank you. Freddie, your point of view?
Well, from our point of view, we have not considered it yet, but we, at least for the techno-economic analysis, we will include it. Because we need to know the actual price of the ammonia produced. We need to know how much is the hydrogen produced. So, but for this, we will consider different scenarios for basically electrolysis, but PEM or alkaline electrolyzers, and then considering if we needed a compression or not, that will also impact on the cost that we actually need, let's say, at the battery limit for our hydrogen. So we will consider it, and this will also be paid in terms of environmental impact. So, but this is one of the topics that we will cover at the end, because we are now just refining the, let's say, the
scenarios.
The scenarios and the synthesis.
For the last speaker, the question is not a question because they were based on production of H2. But Pranav, can you give us your opinion, your point of view on including or excluding H2 production?
Yes. So in our case, our KPI, key performing indicator, or let's say our selling point is different routes of different MOF2s, usage and production of hydrogen. So in which route hydrogen is produced more effectively. So we want to check that. And in order to check that, we have this system boundary from production till the hydrogen production is included in the system boundary.
Okay, thank you very much. And this brings me to another question. So you've mentioned, several of you have mentioned the reference scenario. So the question will probably be to which scenario, if any, you will compare your solution. So maybe we can start with Konrad this time.
I think it goes in the direction of what is the benchmark, I guess.
Yeah.
So in our case, the benchmark is clearly because we are also looking at the feasibility in the railway sector, for example, or transport sector. So our benchmark will be what exists already, like a 700 bar Type 4 tank, where we already saw several advantages of the MOF tank, because a Type 4 tank typically is from carbon fiber, and carbon fiber comes with high costs and also with high environmental impacts. And one big advantage of the MOF tank is that you can use a simple steel tank, for example, which is a Type 1 tank. So it's essentially only steel, because you can work at lower pressures at 100 bar or 150 max. Also compression cooling. Of course, cooling, we have some more impacts, because in a standard high pressure tank, you don't need the nitrogen cooling, but you need also more energy for compression. And this is also where the MOF tank has lower impacts, because to compress to 100 bar, 130 bar, of course, needs less energy than to 700 bar. So the benchmark will be, I guess, existing storage for transport. So not stationary, but mobile tank storage systems. Yeah.
And Javier, what will be your point of view? Do you have the same benchmark or reference scenario?
Yeah, we have a very similar benchmark, because we are also using MOFs, and we are focused on the transportation sector. So the main references which we aim to compare us with are also the compress of hydrogen at high pressure and the liquefied hydrogen.
Okay.
Yeah.
And finally, Freddie, what will be your benchmark scenario? We've maybe lost Freddie. I will ask.
Yeah, I'll comment on that.
Yeah.
So so for in our case, it's a bit tricky, because like I mentioned, we don't have a specific benchmark specifically for photocatalytic hydrogen production. So in our case, the scenarios would be like different routes of hydrogen production, and probably the energy that is being used in the process.
Okay. So quite different from the other approaches,
Yeah.
because your project is a little bit different from the others. The question of data collection was mentioned. So how you deal with this? How the data are collected? Are they shared? Do you have a specific, I don't know, database that you collect with some online tools, or you exchange Excel files with the partners? How, or any other ideas you had to collect and exchange data? So how do you deal with this? For example, Pranav, let's start with you.
Yeah, sure. So for data collection, first of all, like I mentioned, we collect it from our consortia partners, and then the peer review journals get it verified from the experts. So this is from where we collect data. How we collect data, basically, we create open questionnaires where we ask all sorts of questions based on our understanding for every process, for every material and methodology. And then based on that, we developed our system, the input and output analysis for every unit process, and then again get it verified, just to sum it up.
And is it easy to get the feedback? Do the people understand what you ask for, or do you have to have several exchanges in order to refine
Yes.
what you need?
Yes, it's not that easy as it sounds, and it's rightly indicated that people don't speak common language. So exactly what we need for our LCA model development, most of the people are not aware of that. So yes, we have multiple meetings with them. We tell them exactly what type of data and what sort of data we require, and that's why after collecting, after developing this data and even developing model, we share that with the consortia partners, so they also know what exactly what do we mean by that, basically.
Okay. Yeah, thank you very much. I think this is a very difficult task each time. Your point of view, Xavier, Javier, on this data collection? issue?
It's pretty similar. We also collect our data based on the partners of the consortium, which are who made the experimental test and the real trials. It's true that sometimes there are data gaps in the collection of data because the technicians at laboratory do not measure, cannot quantify. They do not have maybe the tools, the appropriate tools to gather all the info that we require. So we also we use modeling tools which give us the support to close the material balances when they are not closed, to estimate energies when they are not given to us. So that's a very useful tool for us.
Okay.
We also later once we have the inventory and we have filled the data gaps, we try to make that we try to validate the results of the simulation, if we have any, from literature sources, so that it's not only an estimation, but a real data.
Okay, thank you. We have Eddie, Freddy, sorry. Can you comment on this? Oh, we lost him.
No, I'm here. Sorry.
Yeah. So what are
Uh,
the difficulties you are facing with the data collection?
Well, as also Javier was saying, fill the gap between what is in the lab, what is we need to actually develop or use in a real case scenario. What are the actual, let's say, yields or as I was mentioning before, what is the, for example, use lifetime for the materials, so that this will allow us to have a more reliable assessment of the technology. So considering, okay, it's with 1 kilo of let's say catalyst, I can produce 100 tons of ammonia or 100,000 tons. I don't know, just to put some numbers. So this is what it's one of the the biggest challenges, and also the actual production of these catalysts or sorbents, because they are synthesized at the lab scale, and a scale up their production will be, let's say, useful to do a more reliable assessment, as instead of, for example, because maybe the data from the lab partners is, for example, I use an oven that the oven has X kilowatt power, so I cannot use that number to synthesize 1 gram of material. So it has a big impact, and it has to be, let's say, scaled up.
Okay, thank you very much. Conrad, if I remember well, you included you go up to the grave analysis, so you've included also some estimation about the lifetime, about the aging of your materials. So how this is treated in terms of data availability and data collection?
I mean, yeah, for the use phase or for the end of life, there is no data yet existing. Yeah, because we don't have it in use yet. So that's why for this you can only do predictions, and of course, or you make a number, you assume a number. And here I think it's important, of course, what you don't exist, you cannot be wrong in the prediction, kind of. But I think for the use phase and end of life, it's important to show different scenarios in the final report, so that at least you can maybe have a look at the minimum and the maximum values.
Okay.
Yeah. Yeah. And for the cradle to gate and for the MOF production, I wanted to mention also 1-2 sentences, because I think a lot of European projects have these difficulties. That you can not only use the lab recipes, then you will have full primary data, very good, but you will be far away from reality.
Sure.
But you can not only make estimations for an upscaling without using any primary data, because then your whole study is completely theoretical. So the challenge is to make a mixture of the both. And for this also LCA is quite useful because you can look for hotspots. You start maybe with the lab recipes from the partners, and then you look, okay, what is in my system the biggest hotspot? For example, I realized that even when you heat a MOF, sometimes MOFs are heated for like 20 hours in an oven. And intuitively, you would think, this takes a lot of energy. But for the whole MOF production, the environmental impact of that heating is very, very low. So it's against the intuition. And most impacts in my case came from the solvent. So then you know, okay, in upscaling, I have to focus on these numbers. Yeah.
And regarding the solvents, I suppose that in the lab scale, they are not reused. They are only used once and then treated as a waste. So how you treat this recycling or reuse loop if you do not have data? Or you maybe have data.
Yeah, no, but no, we don't have a distillation plant for our, which is connected to a MOF plant or something. This doesn't exist yet. But at least for very common solvents, we can look in the literature what is reasonable recycling rates there. And also once the technology is upscaled and really on the market, companies will usually push towards a good distillation. So they would, for example, not recover 20% of the solvent. Then you can also directly don't recover it, you know? So what if you consider solvent recovery, then you can assume some numbers in the 90–80% range of recovery. And yeah, but for this, we rely on literature to model the distillation process. And yeah, I just want to mention, because also when one reads literature from others, often what I also find is that people just take the solvent completely out because they say, okay, most of it is anyway recovered, or I'm working in the cut-off approach. So the solvent is a recyclable. I cut it off from my product system. But this is, I would not say that it's greenwashing, no, because it's just other system boundaries where they say, okay, we cut off the recyclable here. But still, this is like, it's like not talking about one problem. Yeah.
And I would have another question related to the data in all your projects. Did you include the waste treatment in your simulations? Is it included in your, for example, if you produce a spent solvent or acidic effluents, things like this, do you include them? And if you include them, how do you treat it? If maybe Konrad, if you would continue on this point.
That's a very good question. That's a very good question. At the moment, what I do is like when I have recipes, I have the inputs, I know what comes out roughly. So the yield of the MOF, and then everything else, you can assume that this will be like waste. So I have it included, but only as a generic waste stream, let's say. And then you have to decide, okay, either you send the waste to wastewater treatment or to incineration. So this then is also part of the different scenarios how to treat waste from your production. Yeah. But we don't, to more precise answer your question, we don't have primary data on that. Yeah.
Okay, thank you very much. Javier, what do you do in your project?
Yeah, in our case, our process uses quite a lot of a basic solution of sodium hydroxide or potassium hydroxide. So what we do is, well, first of all, we do kind of different scenarios. If we are based on the data that the partners provide us at large scale, all of the solvent, let's say, they disregard this. They waste is a waste. So the first scenario that we do is to propose how we recover the solvent. And then the waste stream that we always have, because we cannot recover 100%, we propose a neutralization with an acid, and then we treat the waste as wastewater, the recovered stream.
I will continue with the question because the time is a little bit running out. Let's see if you have already some results. Do you have already an idea how advantageous will be the solution you are proposing compared to the benchmark? And do you see LCA as a tool for supporting this technology validation or some investment or early market development? So maybe we can ask Freddie. So do you have already some first results and how they are positioned compared to your benchmark?
Well, yeah, we have actually not very reliable results yet. And they are, let's say, under development.
But do you see LCA tool as something that might be a good support for the validation and for the investments and for the market deployment?
Yes, I mean, if the LCA is positive, let's say from the environmental point of view, so this will bring you or give you a very good point to or added value to your value proposition that you have put in your business plan. So that is something that will allow you to add a value to your product or process, whatever you're developing.
Pranav, what is your point of view on this?
Yes, so like I mentioned earlier, we haven't obtained like entire results. We are still at initial stage, but for a long run, if I see LCA is important tool in two important cases. First, material design, and second, as European projects are more focusing, or European policies rather mostly focusing on safe and sustainable design. So there, LCA plays a very, very important role. So yes, LCA plays important role.
Okay. You are all belonging to European projects. So what is your opinion on the standardization effort on the European level? If I noted it well, three of you are using the same methodology, so the product environmental footprint. I think Pranav was using Recipe, so maybe Pranav can start and explain why they're using a different method from the others.
Again,
And is there any need on standardization? If yes, what is your position about the
yes.
standardization?
About method, yes, recipe method we are using, which is when we want to compare it with the literature available. So that then it makes easy for us for the comparison. So that's why we are using it. But again, coming back to the European project, I think yes, we need to have a harmonized efforts in that respect. For example, having central European database for hydrogen production or a common reporting template. So maybe such kind of activities can help synchronize all the projects together. And this webinar could be one of those thing.
Okay. Javier, your point of view on the standardization?
Yeah, same. I think it's, well, we use the product environmental footprint because it's recommended by the EU and in EU projects. So I think there have to be we have to make some efforts all to share the background data sets so that we use the same. We are aligned on the databases and on the impact assessment methods, so we can then reproduce and replicate the studies on each LCA.
Okay. Conrad, your point of view?
Yeah, so I also think that European projects should use the same method. It's also, we have to differ. They are always very picky with words, like the PEF methodology and the PEF method could be two different things. Like the method is what we use to calculate the impacts, and that should be the same. The PEF methodology, however, you have to do a PEF-conform study, but this is more like for products which are already on the market. So using all the method would be already a huge step forward for harmonization. And another one, it was already mentioned, if we would all use the same background database, that would be even better. But of course, we cannot force everyone to use EcoInvent in the background. It's also a private company. But there is this, from the European Union, these efforts to have this PEF database. The current version I don't recommend because it has very old data, like energy data is sometimes from 2010, 2012. But my hope is it will be not for these projects anymore, but the hope is that in 1-2 years there will be the environmental footprint database 4.0, where the
And this will be
commission
free of charge?
I think so. Yes, it's not fixed yet, but the European Commission will be owner of that database, which is also very good. At the moment, the owner was like all the database providers, which made difficulties. So in 1-2 years, there would be hope that also the background database, I'm speaking really about the basic data sets like transport, basic chemicals, and energy, that at least this is harmonized. That would be also very good.
Yeah, thank you very much. And if we go even further, do you imagine that we can have a kind of unique functional unit, as Ashrahat had proposed, or very, I would say, limited number of functional units that can be used? Do you think it would be useful? Freddie, what is your point of view?
Sorry, can you repeat, because I have some background noise, so I cannot hear very well.
That, would it be useful to have a unique functional unit or a very limited number of functional units that would be used in the hydrogen sector? Would it be useful for the standardization, for the comparison?
Yeah, I think so. But yeah, depending on the finalist or the scope of your analysis. But yeah, considering only hydrogen storage as let's say the end, the scope of the technology, I think, yeah, for example, kilo of hydrogen stored, and but I don't know. Honestly, is if it will depend if it's a long or short term storage system. So that also has to be, let's say, clarified or anything, because then it will also depend if it has to be transported or not, or if it's in local. So it's affected for several factors. So
okay. Thank you very much. So before we wrap up, we have one question or two questions in the chat. I'm not sure whether you can answer it exactly, but if you can, which kind of MUF is being used in your respective projects? So can you share the exact nature of your MUF or not? Javier?
Yeah, in our case, I can share that we are using aluminum fumarates and iron fumarates MOFs.
Okay, thank you. Yeah. Conrad?
I don't know if I can share all the linker structures, but for the lab synthesis, we used aluminum-based and iron-based MOFs to also have metals which are not scarce metals.
Okay, thank you. Freddie?
I'm not sure if I can share it, but I cannot also remember it now what is because I actually don't know. So okay. I will need to check. Sorry.
Let's keep it. Okay, Pranav, can you share? Yeah.
Again, maybe I cannot share that in detail. Roxanne is here, so she can scold me on that. But yeah, we use again aluminum and zirconia based basically MOFs.
Okay, thank you. And the second question is about webinar certificates. So I think it's more to the organizers. Roxanne or Sophie, will there be...
For this question, I would need to speak with Estibalis and the ones who did the technical registrations, because we would need to check if this is possible. But we will look into it and get back to you about that. Yeah, thanks for the question.
Thank you. Before wrapping up, I would have some very challenging question to all our speakers. So do you think at the end your data will be comparable? Your results will be comparable? Taking into account the scopes, the functional units, etc. So what do you think, Conrad? Will your results be comparable to the others?
I hope so. So I also want to say again something for the functional unit, because yeah, it's really difficult to harmonize many projects that they all agree on the same functional unit, right? But at least what we can do when we have the final report and we decided for our own functional unit, that we give enough information that people can maybe convert it into other units. Because I will, as an example, the PV sector has a similar issue. Like people are reporting in watt peak, in kilowatt hours, sometimes in square meter of the panel, and so on. And this is not a problem as long as the people share also the conversion factors. Yeah.
So if they give you the key characteristics that makes this conversion possible. Yeah. So Javier, your point of view, will your result be comparable to the others?
Yeah, same. Probably it will be difficult to compare directly the results because of all the secondary data that the data sets and so on that can differ. But if the study is done properly, it should be reproduced and adapted so that we can make it comparable. Yeah.
Yeah, thank you. Freddie, I will let you comment on this also. If you are still here.
Yeah, I'm here. What is the question? Sorry.
Whether your results will be comparable to the others, taking into account the differences in the boundaries, functional unit, etc.
Yeah, I think so. Well, I will leave this more to Esther. That's more in her field, but I think so.
Okay, thank you very much. So the time is up. It's time to wrap up. So we wanted to show you some aspects of the LCA part of different European projects related to either hydrogen storage or hydrogen production. So if you've seen in the first presentation, the keynote presentation of Asharat, the question of the guidelines is really, I would say, of primary importance. So there is still work to do on the guidelines, on the functional units, on the benchmarking, in order to have something at final that will be comparable with the other projects. However, all our speakers have probably demonstrated quite well, I would say, that different kind of approaches can be chosen, cradle to gate, cradle to grave, and this is always in line with the objectives of the given project, but might be then a little bit difficult to compare the projects among them. But there is big will for harmonization, choosing a given software tool, choosing a common, I would say, baseline, and choosing the unique, I would say, evaluation method. So I would say we are on a good way. We are walking in a good direction. There's still plenty of work to do, namely including the use phases and the end of life. which is at the heart of my project, the recycling part. However, I think we are on a good. We are progressing. Maybe some further question. Please address yourself to the organizers of this webinar. And if you there might be, for example, in the future some working groups on these topics or any future collaborations. So please contact the organizers if you want some particular contact, an email, or launch a discussion with somebody. And I have forgotten to tell you at the beginning that the webinar was recorded. So the slides will be shared and the recording will be shared in the near future. And if there are no more other questions,
Yes.
Roxanne, Sophie, I propose to close the webinar.
Yes, thank you, Lenka, very much for your kind moderation, and to all the speakers also. There's one last question, actually, which is a bit out of our maybe project scopes because we are not working, as far as I know, in developing countries. But there has been Navid, who asked what are key parameters in which developing countries are lagging in this hydrogen fuel technology. So I'm not sure if we can really answer that. In my point of view, it would be probably lacking infrastructure and financing often, but maybe also someone else can answer that question. I don't know if anyone can.
I'm not specialist, but I think you are right. Yeah.
Yeah.
Yeah, infrastructure and for example, I'm from Venezuela, and for example, this is a very specific point, and in this case, it's not completely economically viable since we have other source of energy, like a lot of oil or hydro energy. So that's in this is a very specific a specific case. So, but if we then go to, let's say, infrastructure, I think it's one of the most let's say challenges since you have to change everything. And for example, if you go to other countries in which you don't have long water resources or so you cannot have hydrolysis, for example. If you don't have natural gas, you cannot do steam reforming for hydrogen production. So it depends on what is behind it. So
okay, thank you very much.
Thank you. So we will come back to you in the coming days, sending you the slides, the recording, and then you will also have our email address. So if there are any more questions or if you have any ideas also for follow-up webinars, because we are really also interested in keeping the contact between us and of course also everything that's interesting to you. So you can also tell us anything you have in mind for any possible follow-up webinars. And with that, I would say we're at the very end, unless there's something else from anyone in this round.
We can wrap it up. I would like to thank all the presenters and thank the organizers for the invitation. It was my first time doing a moderation, and it was with a great pleasure. Thank you.
Thank
You did it very well.
Thank you very much.
Thank you.
Thank you.
Bye bye.
Thank you.
Have a nice
Bye.
day.
Bye.
Bye.